Hey everyone, I'm Nathan.
I'm Berkeley.
And I'm Charles, and we're going to talk to you about our experiment at Sector 11. Also, this is just a logistical thing. We are half of the team, so the other half will be doing the data analysis. We're just going to talk about the beamline and how we actually did the experiment. So I'm just going to give a brief introduction to powder diffraction, but of course we've seen this a couple times. In general, as opposed to a single crystal, we're diffracting off of randomly oriented crystallites. So what we're going to get is not like spots, but we're going to get rings. This is a Syria standard, and you can see that you get these pretty intense diffraction rings, and you integrate that, and you get your one-dimensional powder pattern. And what's nice about powder diffraction, particular from the synchrotron source, is that you can get data really fast. It doesn't have to be a single crystal, because most things aren't single crystal, and you can still solve the structure. It's just a little harder. So at Sector 11, there's two dedicated powder beamlines. There's the 17 BMB and 11 BM. Essentially, the difference is 17 BM is really high flux, and that means that in powder diffraction in general, you have a balance between resolution and intensity. So if you want really good resolution, you're going to have low intensity. If you want a really intense source, you're going to have low resolution. So essentially, 17 BM uses a 2D panel detector, so it can collect data very, very fast, and it has a high flux of X-rays. But because of that, it has medium resolution, but it's still like orders of magnitude better than your like home powder diffractometer. Whereas 11 BM has a 1D point detector, so what's happening here is your X-rays are diffracting off your material, and then they go through an analyzer crystal, so you're actually collecting that 1D diffraction pattern, but it takes a really, really, really long time, like 6 to 12 hours. So because of that, essentially, 17 BM is extremely good for in situ studies, whereas 11 BM is really good for structural studies at fixed temperatures. Their capabilities, 11 BM is kind of limited. It can really only do temperature, and it can do some gas flow, and you can create your own equipment. They have a custom XYZ stage that can move in all directions if you wanted to do something particular, but that's a little more rare. Whereas at 17 BM, you can do pretty much anything. You do temperature, pressure, flow, liquid or gas, and then you can use a Raman or mass spectrometer to analyze like gas evolution or small molecule evolution. So that's kind of what we did, which is what Nathan's going to talk about.
Yeah, so I guess now that Charles introduced the 17 BM beamline, I'm going to talk about the experiment we actually ran at that beamline, which was an in situ catalytic reduction of copper oxide for solid fuel cell applications. So I just wanted to start with kind of a very basic background to solid fuel cells in case people are unfamiliar. The general idea is you have a hydrogen input, and that produces electricity and water. And generally, the advantages of these are that they're highly efficient, they're stable, and they have long operating lifetimes compared to like conventional batteries. They're also very lightweight and compact and have low emissions. So obviously these advantages are all very nice for a lot of different engineering applications. Some ones you might have seen, here's an example of a hydrogen car. They're becoming more common, but basically you could use them anywhere where you would want to produce electricity. So in our reaction, our like hypothetical fuel cell was using methane gas and water as the input to produce hydrogen. And that's an important reaction because methane's fairly abundant, so it would be a good source for this hydrogen production. However, in addition to the hydrogen, this reaction also produces carbon monoxide, and some of that carbon monoxide byproduct can actually degrade the fuel cell performance over time. And it's also poisonous, so that's obviously bad. So our reaction that we looked at for the powder diffraction experiment was the transition of copper oxide to amorphous copper. And what happens during this reaction is as the copper oxide transitions to amorphous copper, oxygen will diffuse out of the copper oxide lattice and form carbon dioxide. So the final result is that you transform that extra carbon monoxide byproduct into carbon dioxide, which is what we're looking for.
So how actually did we look at these? Obviously, X-rays are a great way to look at structure. So we mounted a copper oxide powder sample into a capillary here, which was then aligned in the beam under helium gas first. And so then we could switch the gas to 5% carbon monoxide and helium, which is similar to those that you would actually see in the cells that Nathan talked about. And so you flow the carbon monoxide over the capillaries, and as you heat the sample, you can then observe, using X-rays, the phase transition from the copper oxide to the copper. 17BM is fantastic for this because it has a number of in situ techniques that can all be used at the same time. So here we were using a gas flow cell as well as a heater to look at the evolution as a function of temperature. It also has an amorphous silica detector, which is extremely fast, so you can watch the images appear on the computer monitor in real time as the transition occurs. You can also look at not only just the image, but also the averaged intensity. So you can see these copper oxide peaks sort of change here at about 180 degrees Celsius into the copper peaks, seen a little bit better in this topological map. So you can see the copper oxide peaks sort of disappear just as the copper peaks appear, which I won't tell too much about because that's the next group's talk, which I'm sure they'll do a great job of talking about. But of course, I would like to thank the Beamline scientists and all of you who have been so great, and the directors of this NX school, and of course Foursquare.
So that's the change in energy divided by the incident energy.
Called the 1.5 times 10 minus 4 medium instead of worse.
Those are the specs that they gave us, and they said that they told me that was better for this application.
I don't understand that.
That'd be a great. I could forward you their contact information. No, I saw that as well though.
Sounds like quantum effect here or something. No, I think something's wrong there. But I mean, with X-ray high resolution, you would eventually can do better than that, even if you do it on purpose. But you're right that they want to balance flux and resolution. But basically, saying the medium one is at 1.5 is a slightly better number than 2. I mean, the lower the number is better, your delta E is better. So something is wrong.
I think it's due to and if you look at the actual energy, so you're dividing by a larger number, right?
Oh, maybe it's.
Yeah, so.
Well, so 50 kilovolts.
Yeah, so it's the difference. That's an average. We got those from the specs that they supplied online. I don't know if those are updated.
Yeah, well, basically they're the same, really.
Yeah.
Experimentally, how do you ensure that you have a random distribution of grains in your sample?
That's a good question, Brian. Essentially,
So I know they were finely ground.
essentially, you just grind your powder for a long time, but you'll never obviously get an infinite orientation. Is really important because so you don't want to pack these too tight, otherwise you can actually force a thing called preferred orientation. So you want to lightly pack them. You want a really, really well ground sample. They actually have a recommended size. But it's sample dependent.
Did you guys load the capillary yourself?
We watched someone load it. In the back?
Yes, we did.
So yeah, a lot was going on. So the capillary was rotating as a gas was passing through it, as it was being heated, as we were passing X-rays through it. Which is why 17BM is so good for that. Also, 17BM is in sector 11, but it's not physically there. In the umbrella that is Sector 11, like jurisdictionally, it's there, but they call it the Alaska of Sector 11 because it's physically removed. Essentially, there was an open beamline, so they took it. Any other questions?
Both those 5.